Next series in revision for electricity. Today we're going to cover about series and parallel circuit, especially how to calculate the effective resistance, current, and potential difference using Ohm's law. Okay, first let's examine the question. Calculating the effective resistance is very important in this topic because it tests your understanding how the series and parallel circuits work. So basically, most of the cases we want parallel circuit, but some of the cases mixing both series and parallel might be optimized, might be the optimal solution for our daily life situation. So let's examine the first circuit here. We have to determine the effective resistance. Okay. So here we have two resistors connected in series because they are immediately right beside each other. So for series, the REFF is actually we just need to add both resistance. So basically what we do here, these two resistors equivalent to one resistor but longer wire in terms of, let's say that the factors of resistance here. Let's revise the factor of resistance. Rho L over A. So basically L is the length, A is the cross-sectional area, and rho is the resistivity. So what it say here that if the length is longer, then the resistance is higher. So that means that the length is directly proportional to the resistance and inversely proportional to the cross-sectional area of the resistance. So since, let's assume that this first resistor here is a piece of constant wire, and then we connect right beside it another constant wire. So basically we increase the length of the constant wire, thus we increase the resistance by adding the two resistance value. So it's equivalent to 20 ohm plus 20 ohm. So the REFF here is 40 ohm. As simple as that. So we just add the two. Imagine that the two resistors represent one constant wire, but if we connect it in series, then the constant wire become longer, thus the resistance become higher. Okay, number two, we have two resistors here in separate path, but are beside each other, but in the separate path. So we have path A here and then path B here. So we call it in parallel arrangement. So in this case, if we assume that one resistor is a constant wire, then if we combine two constant wire, it will become larger cross-sectional area. It will become thicker. The constant wire connected in parallel means that the total cross-sectional area is increasing. Thus, the resistance will decrease because of the inversely proportional relationship. So what we're going to do here, actually, we have to make it 1 over something because the A here is 1 over something. So the formula gonna be 1 over R1 plus 1 over R2. So make sure that after you compute the values of this formula here, make sure that you flip it at the end to get the real value of REFF. So let's find that value first. 1 over 20 plus 1 over 20 become 2 over 20. So if we flip it, it becomes 20 over 2. So we have to flip the values here because this value 2 over 20 is just 1 over REFF. What we want to find actually is the solely REFF without the 1 over. So I have to flip it. 20 divided by 2 is 10 ohm. So what we observe here, if the resistors connected in series, the REFF is much higher than the single resistor itself. So it's much higher than 20. But if the resistors connected in parallel, the REFF is much lower than the single resistor, which is 20 here. So it will become lower. So keep that in your mind, that in order to know your answer is correct, you must check if the value is higher than single resistor or if the value is lower than the single resistor. So let's move on to question number 3. We have here all 3 resistors connected in parallel because each resistor has its own path. 1 path, 2 path, and 3. So, but the second path has an open switch, which means that the current will not flow through here. So, not flow through here. So, what we need to account for is just this resistors and this third resistor. So, basically, has the same value as the question number 2, which is 10 ohm. So 1 over 20 plus 1 over 20 is 2 over 20. If we flip that, 20 over 2 becomes 10 ohm. So basically, it's just the same as number 2. So make sure that if you see a switch here, then it's in open state, which means the switch is closed. Oh, not switch is closed, switch is off. So it means that current will not flow, and thus the value of the resistor here is not count towards the REFF, the effective resistance. So let's see number 4. Here we have a combination of series and parallel, but we must recognize that these two here is in parallel arrangement because it has its own path, whereas this one here is series with these two, because if we follow this path over here, this 20 and 10 here are exactly right with after right beside them, each other. And also if we follow this path over here, these two over here also immediately beside each other. So basically we have two paths, but we have to solve for the parallel arrangement first. So what we're gonna do, we will draw a new circuit that look like this. This is the 10 ohm, and this one is the new REFF by considering 20 ohm and 20 ohm in parallel arrangement. So we already know that value before, this just 10 ohm because we calculated before. If two resistors which each has 20 ohm connected in parallel, we get 10 ohm. Then we assume the same case here. These two resistors are connected in parallel, so both has 20 ohm. If we add them, 1 over 20 plus 1 over 20 become 2 over 20. Flip it, 20 over 2 becomes 10 ohm. Now we have a new arrangement of circuit, which in case both of these new resistors are connected in series. So we can do that easily because when we connect it in series, we assume that the length is increasing, thus the resistance is increasing. So we need to add. So 10 ohm plus 10 ohm become 20 ohm. So that's our answer for the final effective resistance. So let's move on to number 5 here. So now we have to look at this question carefully because this is not the same as the before. If we look here, this 20 here and the 20 here are connected in parallel arrangement, but this 10 ohm here only related to this 20 ohm here. So let's draw our uh, path first. So plus minus, the current will flow from positive to negative. So it will go to this loop here first, and then the current also will flow through the second loop here. So when we do that, we immediately recognize that in the first loop, we don't cross the 10 ohm resistor. So the 10 ohm resistor does not involve, does not have any relationship with the 20 ohm resistor here. But in the second loop here, the second path, the 10 ohm and the 20 ohm are immediately beside each other. So after the current leave the 10 ohm, it will go into the 20 ohm. So we say that this 10 ohm and the 20 ohm are in series. So what we should do, we should compute these values first before we calculate the effective resistance. So it's basically the new circuit gonna be like this. If this is the 20 ohm and the new resistor at the back is 20 plus 10, 30 ohm. Because in series, we have to add it, assuming the length become longer. So now we have the new arrangement of circuit here, which the back we already count up the 20 and the 10 ohm. So now this is basically plain parallel arrangement. So we can do the 1 over formula, 1 over 20 plus 1 over 30. So if we want to calculate it manually, then you have to make common denominator. We times this by 3 times this by 2 become 3 plus 2 over 60, which is 5 over 60. But that is not the answer we're looking for because we need to flip it. So 60 over 5, which is 12 ohm. So this is the final answer. So make sure that you don't leave your answer in fractional form. You must convert it into a single number or decimal form. So this answer here, if you leave it as it is not acceptable in SPM. And of course, you need to include the unit ohm here. Okay, so let's move on to the next question. This is look like a complicated one, but doable if you do it carefully. So basically, let's examine how many paths that we have here. So let's assume straight path first. If the current flow from here, we assume this is the positive end and this is the negative end. So if the current start from here, it will go through the 20 ohm first and then 20 ohm the next one. So this is the first path. So which means that this 20 ohm here and this 20 ohm here are connected in series. So let's investigate the next path. So if the current flow from the same positive end and then it encounters a junction here, so it will go here and then go here and then go to the 20 and back to the negative. So this is the second path here. So what should we do first? We should clear up the second path here. Okay, how are we going to do that? So let's draw the new arrangement. So basically, this is the straight path, and then we have just before the last resistor. So make it longer like that. So basically, we have this 20 ohm here, this 10 ohm, and this 10 ohm. This is also 20 ohm. So what I did just now, I make it look. It looks like a series 10 and 10, sorry, 10 and 10 look like in series, but in parallel with the 20 ohm above. Okay, so we see clearly that we have to clear this one first. So like always, like usual, if the resistors connected in series, then you need to add up. So we can clear that. It becomes just a single resistor with 20 ohm. Now we have two resistors, the new arrangement here. These two resistors here are connected in parallel. So we already calculate that before. If we just make it one resistor, it will become 10 ohm. Because 1 over 20 plus 1 over 20 become 2 over 20. We flip it, become 20 over 2, which is 10 ohm. Now we can add up these two resistors because this is just a plain series connection. So the REFF here is 10 plus 20, which is 30 ohm. So make sure that in order for you to solve this problem correctly, you have to trace the path first. If you see a complicated path like this, then you might need to solve it first before you solve the simple plain one, because the simple plain one needs to be the final steps in your calculation for the REFF. So if you encounter like this, you can redraw it if you cannot see it clearly. But for me, this is just a series circuit down here. And then this series circuit is parallel to the 20 ohm right here because we have junction here. It stopped after the 20, not after this 20. So if this wire here is connected after this one, then we have this type of arrangement. So basically these two resistors here are parallel to these two resistors down there. So this one need to be has different effective resistance than this one here. So you must make sure that the connection ends where. If the connection ends here before this one, then you need to make this one the final step. So make sure that you leave it alone until the end. Take care the first thing first, the complicated one first, before you do the simple one. Okay. So let's move on to the next question, number 7. Okay, this is more complicated, but we can make it simple as we redraw it. We need to redraw it to make it clear. So let's trace the path first. So if we assume the X is positive, the Y is negative, so the current will flow through the 7 ohm and 3 ohm and back to Y. So this is the first path. The second path is it will flow through the 4 ohm, 6 ohm and back to Y. So this is the second path. So what we recognize here, we see that the 7 and 3 are series arrangement, are in series arrangement because it has the same path. Same with the 4 and 6 are in series as well. But these two paths here are in parallel because it's separate path. So we can solve the first loop first or the second loop first because it doesn't matter. It has the same amount of resistors. So we can solve it uh, independently. So let's solve for the first one first. So if we redraw that, it will become like this. And then the second one will become like this. Okay, so this is the X and then this is the Y. So basically series we just add up 7 and 3 become 10 ohm, and the series below it also we need to add up 4 and 6 also 10 ohm. And now we have a very simple parallel arrangement, so we can use the 1 over REFF, 1 over 10 plus 1 over 10 become 2 over 10. We need to flip it, 10 over 2 become 5 ohm. So this is the final answer. So make sure that As I repeated very much, as I repeated, we need to trace the path first and consider which are in series and which are in parallel. Solve the complicated one first before we do the final step, the simple one. Okay. You might say that 7 and 3 in series is not that complicated, right? So why we need to solve 7 and 3 first? Because the final one is in parallel. So the final one in parallel is more complicated. If not, we solve it in series first. So we need to make it less complicated by solving the series first, and then we get more simpler one than the if we want to solve for the parallel directly. Okay, so let's move on to number 8. So number 8 also looks like very complicated, but it's not that hard. Like usual, we have to trace the path first. Assume that x is positive, y is negative. So if we go to the above 4 and then go to 2 and then back to negative. So this is path number 1. Path number 2 is just plain straight. Path number 3, so this is just straight. Path number 3 is below. So we have 3 paths. We know that all these 3 paths are parallel to each other. So let's solve for the series. Because we have at the end parallel, all are parallel. So we have to solve for series first because we need to make it simpler. So we can redraw this circuit over here into 3 lines. So the above one, the second, and the below. The middle and the below. So it look like this if we want to make it simpler. So this is 4 ohm, 2 ohm, 6 ohm, 2 ohm, and 4 ohm. So let's solve path 1 first. If we add up, then it becomes 6 ohm. So remember that the above, the top one is 6 ohm, the below one also 6 ohm. So now we have 3 identical resistors connected in series. So all has 6 ohm value of resistance. So we can use our formula here. 1 over 6 plus 1 over 6 plus 1 over 6 become 3 over 6. Don't forget to flip it. 6 over 3 becomes 2 ohm. So this is the final answer. So now we have to make sure that our complicated diagram over here, you must recognize the loop or the path. And then if we have 3 paths or 2 paths, that means the end gonna be the parallel connection, parallel arrangement. That means you have to solve the series first. Okay, same if you back here, why we have 2 separate paths, right? But why we solve the parallel first, not the series first, like the others arrangement, the other equation like 7 and 8, because these two here, 20 and 10, 10 here, share the same path with this 20 here. So basically, we have series path at the end. That's what I mean. Because they share the same path with the 20, the end one. So that means that we have to solve the parallel first. But if we want to solve the parallel first, we have to consider the series in the parallel as well. So like the same procedure here, if we encounter 2 or 3 more paths, then we have to solve the series in each path. So let's see. One, we have to leave the 20 ohm alone because that is the final step. Because 20 will pass 20 here, will go to 20, and this below here, these two 10 ohms resistance also will cross the 20 after. So we need to leave it at the end before after we solve this complicated circuit before it. Okay, before the 20 ohms. So we make it as is not exist first, then we just leave with 20 and 10 10, which is also have two paths, but we have to clear the series in the parallel. So this is series 10 and 10, so we need to clear that first, and then we get two resistors in parallel, then we can clear that as well, and then we can look back at what we uh, cancel earlier. So we need to include it back lah. So don't forget about that, because this is still count towards the REFF, which is plain series. So on the algorithm here, the way we want to solve it, so let's summarize it. First, trace the path. So if we have two or more paths, clear the series in each path. If we have path sharing resistors, we have path that share the same resistor, like number 6 before, then we need to leave that resistor at the end. Okay, so that is our algorithm here. This third condition here is quite difficult to identify, but if you do a lot of practice, then you know which how to do it, how the shape of the problem, the form, the type of the problems that involve this third type of situation here, condition here, that we need to leave that resistors alone first. We need to clear before we go to the last one. Okay, so let's move on to the next topic here, still in series and parallel circuits, but we go to the potential difference, the concept of potential difference. So basically, what is meant by potential difference? So potential difference is the work done to move 1 coulomb of charge across 2 points in the circuit. So that is the definition for potential difference. What it means actually is that if we have assume that we have a mountain here, the water will flow from higher to lower. This is higher potential energy. This is lower potential energy. So the difference between the potential energy, we call it potential difference. So the water will flow always from higher potential to lower potential. So higher potential, we make it symbol positive, lower potential negative. So same as heat flow as well. So heat flow, if we have a conductor wire, this is the hot one. Hot. This is the negative cold. So hot has higher potential, cold has lower potential. So the heat will flow from hot to cold, from higher to lower potential. So the difference between this potential is potential difference. So in concept of electricity, so we have a resistor here. So this positive terminal here is higher potential, negative terminal here lower potential. So for example, this is 1.5 volt battery potential difference. So the higher potential has a value of 1.5 volt, and the negative potential, the lower potential, always have 0 volt. So the potential difference is 1.5 minus 0 become 1.5. So that is the potential difference. The amount of charges, let's assume this one single charge here. One single charge, electron. One single charge, electron. If we want to move this electron from here to here, from this is the positive, this is the negative, from here to here, these 2 points here, then it requires potential difference. The work done is the same as the potential difference between these 2 points, which is also 1.5 volt. Okay. Because this positive here connected directly to this positive, so this has 1.5 volt. This negative here is connected directly to the negative terminal. This has a 0 volt. So the difference between these two values is 1.5 volt, also known as the potential difference. So it's basically the same meaning as voltage, but the voltage itself consists of different types. But this term here, the potential difference, only refers to one type of the voltage, which is the voltage between 2 points here. Any 2 points on the circuit is called potential difference. But we can also um, call it voltage like normal, but as we're gonna learn after this, that the voltage has a very different types as well, such as the internal voltage, the total voltage, the EMF, also known as the total voltage. It has a different definition for it as well. Okay, so basically that's the concept of potential difference. Every time you have a potential difference, then they have a flow, either flow of water, flow of heat, or flow of current. But in this case, in this chapter, we will learn about flow of current, always from positive to negative. But the electron is opposite direction, negative to positive. You have to keep that in your mind. The current is from positive to negative. The electron is negative to positive. Okay, so let's move on to number 2 here. Given the value of V1 and V3, 4 and 5 volt, 4 and 5 volt respectively. Calculate the value of V2. So again, the total volt, the total potential difference here is 12 volt. So this is the positive terminal, this is the negative terminal. So positive terminal is connected directly to this positive side over here. So we can label it positive as well. And then this negative here connected to this side, directly to this side here. So here we have this positive 12 volt and this is 0 volt. So the potential difference between these three, which is this 2 point here, include the three resistors, is 12 volts. So 12 minus 0 is 12 volt. So that means that the total potential difference for each resistor must contributes to 12. So we already have 4 and 5, which are equal to 9 volts. So the rest, the remainder, must be 12 minus 9, which is 3 volts. Okay, so the V2 is 3 volts. So if we want to find the potential difference point by point, how much the potential difference drop until 0 here? So 12 minus 4 become 8 at this point. 8 minus 3 become 5 at this point. So 5 minus 5, 0. Then we have completed potential difference loop here. Okay, let's move on to number 3. V1, calculate V1 if V2 equal to 3 volts. So let's always positive and negative. The total is 9. So this is the positive side. This is the negative side. So the positive got 9. The negative will get 0. So the potential difference between these 2 points here is 9 minus 0 is 9 volt. So that means that the total voltage for all these 3 resistors here that included in these 2 points that we already picked earlier must must sum up to 9 volt. So we already have 3 volt here. That means the remainder is 6 volt. Okay, that is the total potential difference for these 2 resistors here. So we cannot know what's the value for each resistor because we don't have enough information to know each resistor. But we can assume that this is 3 volt, this is 3 volt if all of these 3 resistors here are identical. We can assume that. So let's check that 9 minus 3 becomes 6 volt here. 6 minus 3 becomes 3 volt here. 3 volt minus 3 volt becomes 0 here. Okay, so completed our loop. Okay, let's move on to number 4. Calculate V2 if V1 equal to 6 volt. So V1 is 6 volt. So let's make the positive and negative. So positive here, negative here. So 9 volt here, 0 volt here. So the potential difference between these 2 points, this end and this 2 end is 9 volt. But we already have 6 volt over here. That means the rest, the remainder is 3 volt. Okay, as simple as that. So as we look over here, this is the parallel arrangement. We know that if the resistor connected in parallel, then the potential difference is the same. And why is that? Because this point here, we already label it positive, higher potential, same as this point over here, also positive, because it's connected directly to this positive here, and this positive here also connected directly to this point over here, the terminal positive. Or you can say that this point over here is connected directly to the terminal positive terminal. So it has the higher potential values. So 9 volt. So these 2 points here share with these 2 resistors. That means the starting point for the above and below are the same, 9 volt. But at the end, we got 6, we have a potential difference of 6 volt. That means 9 minus 6 is 3 volt over here. So 9 reduced to 3 volt. So both resistors use 6 volt, because it started with the same value of potential and end up with the same value of potential. And then this potential here, minus 3 volt, will become 0 volt at the end. So that's why these 2 resistors here connected in parallel has the same potential difference, because the point of starting point is the same for both, even though they have separate paths. So what's the difference is the current flow. The current flow from the above and the current flow from the below will be different if the value of the resistors are different. The value of the resistance are different. But in case we assume it's identical, then it's gonna be the same. The current will also be the same values. So let's move on to number 5. Diagram shows a circuit with 3 resistors. Okay. If the resistance are identically same, find each potential difference. Okay, so we have 12 volt here, plus and minus. So plus here, minus here. So 12 volt here, 0 volt here. So when we deduct 2, it becomes 20 volt. So this is the potential difference between this point here and this point here, these 2 points. So inside these 2 points, we have 3 identical resistors that sum up to 12. That means each resistor will have the same value distributed equally among each other. So 12 divided by 3, which is 4. So each resistor must have 4 volts in order to get the sum up of 12. So we already calculate that. And then if you want to check it one by one, 12 minus 4 is 8 volt here. 8 minus 4 is 4 volt here. 4 volt minus 4 volt, it becomes 0. So we check that, we completed the loop. B, if the cell is replaced with 36 volt, the resistors are identically the same. Find the new reading. Again, if we replace this with 36 volt, then this here have 36. This still have 0. 36 minus 0, it becomes 36. So now we have to make a new value of potential difference for each resistors. Again, the same 2 points divided by 3. So each should have 12 volts. Each 12. So if we check back, 36 minus 12, it becomes 24. 24 minus 12 becomes 12. 12 minus 12 is 0. So we completed that. So let's move on to number 6. Given the circuit contains 3 resistors, okay, if V3 equal to the 3 volt, what is the potential differences observed on V1 and V2? So again, plus minus 9 volt is the total one. So this side over here is directly connected to the plus. This side is directly connected to the minus sign. So this is 9 volt. This is the 0 volt. So the potential difference between these 2 points here is 9 volt. So the total between these 2 points must um, contributed to the 9 volt. We already have 3 volts. So that means the remainder must be 6 volt. Again, parallel. These two resistors are in parallel. That means they share the same start and end point, which means that the potential difference going to be the same. Okay. So the V1 is equal to V2 is equal to 6. Okay. Same 2 points means same potential difference. Different paths, different current. Okay. Same path doesn't mean have same potential difference. So let's, for example, we have this path over here. Okay, we have the same starting point, point A and point B. So assume this is positive, this is negative. So this path here, path number 1, and then this is path number 2. These two paths, if we have two paths, then we know it's parallel arrangement. But the first path here, resistor 1, resistor 2, and this is resistor 3. Let's label it. That means the path 1 and path 2 share the same 2 points, thus has the same potential difference. But this path here, the first path here, 1 and 2, each resistor has different potential, different values. Because if we assume that this is the 6 volt, then 1 and 2 contributed to the 6 volt, 3 also contributed to 6 volt. So 1 and 2, like I said, contributed to the 6 volt. That means each individual resistor has different potential difference than 6 volt. That's what I mean. If the resistors are not identical. If they are identical, then there are the same potential difference, but still not 6 volts. Maybe this is 3 volt and this is 3 volts. Okay. Or this is 4 volt, this is 2 volts. What kind of combination that will give us the 6 volt? That's what I mean. If the resistors in the same path, that means doesn't mean that it has the same potential difference. So that's the conclusion. But if the two paths share the same 2 points here, then these two paths each has the same potential difference. Okay. So let's move on to the final subtopic, current. So what is meant by current? Rate law of charge. Because we already defined the formula for current, we q over time. Every time you have over time, that means it's rate of something. Rate of velocity, rate of displacement, rate of momentum or something like that. So if we have charge above, that means we have rate of charge, rate of flow charge. Okay. Number 2. If the current flow is 25 ampere, what is the reading for A1 and A2? So for the rule for calculating current, we have to trace the path. So we don't need to the positive or negative, but it will be helpful as well because we need to know the direction of current. But the value of the battery is not needed here. So if we label is positive, negative, like always, then we have a current path that flow like this. Only one path, that means they share the same current. So remember that one path has the same current. So if we have 25 ampere over here, that means 25 ampere over here as well, and 25 ampere here as well. So same path, same current. Same path, same current. Or we say that series. Same path means that they are in series, same current. Different path, different current values. Okay. And both, all of these, and since there are only one path, they share also the same 2 points. So they have this, not the same. They have a total of potential difference same as the battery. That's what I mean. I may need to be careful here because the potential difference for each point in the path is not the same. We already cleared that before. But the total potential difference along that path must have the same value as the battery because the 2 points are the same. The 2 points that include all the things inside it are the same. So number 3, if the resistances are identically same, what is the reading for A1 and A2? Okay, let's trace the path. So we have first path, we have the second path. So since we have different paths, it might have different value of current. But since it also stated that the resistance are identically the same, that means each path has same amount of current. So doesn't mean that it will have. So I'm gonna make it clear. So what I mean, if the 2 paths have the same or resistance, has the same current, doesn't mean that it has the same value as 20 ohm because this 20 ohm here is the total before it enters the first and the second path. So what I mean is basically that this one first path and the second path share this 20 ohm here before that split. So the 20 ohm here come here and then they can split. That means that distributed the current equally due to same resistance. So we can say that this A1 here should be 10 ampere. This A2 here is already merged back. So this is 20 ohm and 20 amperes. So this each path has 10 ampere. The below path also has 10 ampere. If we add up that, then the A2 should be 20 ampere as okay. So let's move on to number 4. If A1 is 10 amperes, what is the reading of A2? So let's trace our path. So let's say that our path start from here. We have first path and then we have second path. You should do from positive to negative, but we make it simplified because both this path and this path here are shared by these 2 paths. So basically we have 50 amperes total that needs to be distributed between A2 and A1 here. A2 in the first path, A1 in the second path. So we already know that A1 has 10 amperes. That means the remainder must be 40 amperes. Okay, to make a total of 50. Okay. If current flow to R1 and R2 is 25 ampere and 13 amperes respectively, calculate the current to R3. Okay, so we have 25 ampere and 13 ampere. This is the first path, this is the second path. These two paths here merge here and here. That means they become one. So 25 plus 13 become 38 ampere. R3. So number 6, compare I1 and I2. So we don't have the value here, but the rule here, current likes smaller resistance. Current likes smaller resistance. Current like to flow. Yeah, smaller resistance. So prefer. So I can say prefer. Current flow prefer smaller resistance path. Okay, so which one has the smaller resistance path? Here, let's make I1 is bigger than I. So it's kind of logical here because the current flow represent the smoother the movement. If we have a lot of resistance, then the flow is not smooth as the lower resistance. So it becomes smaller current values or the higher resistance. And the current prefer smaller resistance. Okay, number 7, which bulb is removed? All the bulbs cannot light up. Okay, so we have to recognize which bulb. If we remove it, then all the bulb will not light up. So if we remove this bulb over here, so we have positive, negative, so the current will flow from positive, and then we block here. The current cannot flow through C, D, and B. So that means that if we remove A, then all cannot light up. So let's examine other bulb as well. So if we remove B, that means that the current can still flow through A, but it will not flow through B. It will still flow through C, D, and back to negative. So this is not the case here. It says the question all must not light up. So let's examine another bulb. If we remove this bulb over here, that means the current will not flow through the C, but it will flow through B. So still as a bulb that light up A and B. Then if we remove D over here, that means the current can flow through A and B, and also current can flow through C, but blocked by D. So still there is some bulbs that lights up. So what our answer is, we need to remove A. We need to remove A so that it block all the bulbs. So how about number 2? If we remove A, this is the positive negative, the current can flow below and back to D. So we will not go through the path A. So let's erase that. How about B? Again, the current will go up and back to D. So that's not what we search for. How about C? So the current will flow through A and D. The current will flow through B but block back C. So still not the correct answer. So how about D? So if we flow to the path A, then it's blocked. Path B and C also blocked. So this is the correct answer here. D. Eight. which bulb is removed, the other three bulbs still can light up. Okay, that means that if we remove one, then the other bulb can light up. So that means that we can, this is the same arrangement as before. We can remove B, we can remove C, but not simultaneously. That means that either we want to remove B or remove C or remove D. Still, A and B can light up, or A, C, D can light up. Same like here, we can remove A, we can remove B, or remove C separately, not together, not together. So that either if we want to remove A, B, C, D light up. If we want to remove B, A and D light up. If we want to remove C, A and D light up. Okay. But it said that either three bulbs still can light up over here. So we have to take care three bulbs. So we just need B, only B here. Because this bulb and this bulb can light up. So let's agree examine the below. We just need to remove A. So we just need to remove A because we need three bulbs. If we remove A, B, C, and D. Okay, so now I understand the question. Okay, that's all for today. Hopefully that you understand how to find the effective resistance, the algorithm to find the effective resistance, the concept of potential difference, and preference of current flow. So if they share the two same points, then the potential difference is the same. If they share the same path, then the current is. Okay, that's all for me today. Thank you.